Reducing radical expressions involves taking expressions involving things like square roots or cube roots, etc., and trying to extract from them any additional powers that are under the radical. For example, let's start with discussion of the square root function. The square root of x returns the non-negative real number whose square is that number x. You should think of it as the inverse operation of squaring. If you square a number, it gets multiplied by itself, and when you ask for the square root, you're asking for the non-negative number that you would have to multiply by itself to get the result that you started with. For example, the square root of 16 is of course 4, and the reason for that is if I was to take 4, it's non-negative, and if I was to square it, I would get 16. Note that minus 4, with parentheses around it, and if I square it, also gets me 16. But the square root of 16 is not negative 4. The symbol, this radical symbol over the 16, is preferring the non-negative number whose square is 16. And in this case, it's positive 4 and not minus 4. Now, what we're doing when we calculate the square root of 16 is we're observing that it is the square of a nice number. It's the square of the integer 4. So what we're doing is we're thinking to ourselves, okay, 16 is 4 squared, and when I take the square root of it, I return the number that's being squared. In general, we want to say that the square root of a square, in other words, the square root of x squared, is x itself. Same principle above. I squared 4. I took its square root and I returned 4. Here I square x and I take its square root and I return x. But of course we have to be a little bit careful here in the case of even powered radicals like square roots, because if I apply this principle to minus 4, I don't get negative 4 back. In fact, as we saw above, the square of that will be positive 16, its square root will be positive 4. So because this symbol square root is preferring the non-negative square root, we need to take the absolute values to ensure that we get a positive result. The absolute value of minus 4, of course, is 4, and that's what we would expect when we take the square root of 16. So to make our equation above correct, we need to put absolute values around the x, and now it is true not just for non-negative numbers, but for negative numbers as well. It's true for all x. Let's look at some more examples. Let's reduce the square root of 8 times x squared. I'm multiplying 8 and x squared, so what I'm looking for are any squares under the radical. And I'm going to write 8 as 2 squared times 2. It's 2 cubed, so I have to square 2, that's 4, and I double that, it gets me 8. X squared is already a squared. And then I'm going to take out the 2 from the 2 squared here. I'm going to take out the x here, and then I'm going to be left behind with 1 factor of 2 under the radical, and that doesn't reduce any further because there's no squares hidden inside the 2 that we can extract. Now this expression isn't quite accurate right now. If I plug a negative number in for x and square it, it will become positive. I can then take its square root, and the number I'll get as a result will be the non-negative one. So to ensure that I'm getting the right sign here when I'm done, I better take the absolute value of x to ensure that they agree. Here's another example. Let's reduce the square root of 16 times x cubed. Now I'm going to look for squares under it. So 16 is 4 squared, and then x cubed is x squared times x. I'm going to extract each square outside the radical. So the 4 comes out and the x comes out, and we have this principle where we should use absolute value, and then we're left with the square root of x under the radical. Now, in this particular case, because I started with an odd power of x under the square root, when I cube a negative number, it will stay negative, and I shouldn't be taking the square root of that anyway to begin with. So in this case, the domain of the expression is only including non-negative numbers. X has to be greater than or equal to 0 for this expression even to be defined. In which case, if my number that I'm using is never negative, the absolute value really doesn't accomplish anything, and we can drop it. The square root of 16 times x cubed is just 4 times x times the square root of x. And that's valid for non-negative numbers only. Here's one more example. Let's reduce the fourth root of 16 times 8, or x to the 8. This is a fourth root now, and the principle is the same. We're looking for numbers that we're raising to the fourth power. Just like a square root, if it's an even power, like to the fourth power, I need to make sure I'm working with absolute values when I extract powers of x outside. I'm always going to get a non-negative result when I take even powered roots like a fourth root. So 16 is 2 to the fourth, 2 times 4 times, or 2 times 2 times 2 times 2, that's 2, 4, 8, 16. And then x to the eighth is x to the fourth times x to the fourth. I add exponents when I multiply, so that gets me x to the eighth. Each one of those can be extracted outside the radical. So I get 2 outside, I get an absolute value of x from the x to the fourth, and I get another factor of absolute value of x. Everything is being accounted for, everything has come out of the radical, and there's nothing left behind to write under the fourth root anymore. If you like, there's fourth root of 1, and that would just be 1. And so in the end, I have x times x in absolute value being multiplied, so that's really just the absolute value of x squared. And if I square a number, if it was negative or positive, squaring would guarantee that the result is positive anyway. So there's really no need for the absolute value in the end for this example, because the resulting absolute value was squared. 2 times x squared is sufficient here. This is always going to be non-negative, and having the absolute value really doesn't accomplish anything. Let's look at some odd roots, so cubed roots, for example. The principle here is exactly the same. The cubed root of a cube is that number that's getting cubed itself. So if I've got x cubed under a cubed root, I just report back x. This works, however, for all x. When I'm working with an odd radical like cube roots, fifth roots, etc., I do not need any absolute value here. To see why that's the case, just think about a negative number. I can happily take the cube root of a negative number. In this case, this is the cubed root of negative 2 being cubed, and I want to keep that negative there. And because it's an odd power, when I raise it to the third power, I'll still retain that sign. So I'll get negative 2 back as a result. If I look at the cube root of 16 times x to the fifth, I look for any cubes under there. So 16 is 2 cubed times 2. It's 8 times 2. X to the fifth is x cubed times x squared. I'm adding exponents. Every cube I can bring outside, so it's 2 and x. And then what's left behind is the cube root of 2 times x squared. And those cannot be reduced any further. Again, there's no need for absolute value. If I plug in a negative number here, I'll have a negative result. And outside, I'll have a negative number as well, and I want those signs to agree. Putting absolute value there would make everything positive on the right, and it would no longer agree with the left. Let's look at another example. Let's reduce the fifth root of x to the 10 times y to the sixth. Now I'm looking for fifth powers. X to the 10 is x to the fifth times x to the fifth. Y to the sixth is y to the fifth times y. Every fifth power comes outside. And I'm left with one factor of y under the radical. And again, this is an odd radical, fifth root, and so there's no need for absolute value here. I get x squared times y times the fifth root of y. Here's an alternative way of doing the calculation here. You can work with exponential notation if you prefer, and it will easily calculate the appropriate exponent using properties of exponents. So this is now x to the 10th times y to the 6th raised to the 1/5 power. I can then apply that exponent to each factor because I'm multiplying here. So it's x to the 10th raised to the 1/5 power times y to the 6th to the 1/5 power. I'm taking powers of powers, so those can be multiplied. Multiplying 10 times a fifth gets me 10/5. Multiplying 6 times a fifth gets me 6/5. Simplifying, I get x squared. 10 over 5 is 2. And if I divide 6 by 5, I'll get 1 plus a fifth. That gets me x squared times y. y to the first, that's that one factor of y that we had outside, and then y to the fifth gets me a fifth root of y. I'm adding exponents, so I'm multiplying those individual factors together.